this is about let's discuss about dilated convolution. So what dilated convolution will do is it will try to extend the reception size. Okay, so we have discussed before that like receptive field size is depending on our filter size, right? As your filter size is low, actually it will go more resolution, right? So and it will try to have much more reception than using a larger filter size. So using something like this will only do like this, it will only have something like this. But if you use a smaller filter size, it will have much more better receptive size. So taking this into consideration, in case if you have a constraint like you can't use smaller filter size, okay, so if such kind of thing is there, but in case if you want to do a better way, so what you can do is use a dilated convolution which actually extends the reception field size. Okay, so with but this one more beautiful thing with this is with no increase in parameters. It doesn't do any parameter increment, it uses this. And then what actually dilated convolution will do is it's something like this. So you have value here. Okay, let me give a sample of values here. So -203 something randomly I'm giving it. Okay, so 44201. Okay, let me take these values, and out of these values what will happen is, so it will try to do a kind of a convolution. Let me do it here, do a dilation. So what it will do is, so if you take this as input, okay, treat this as input here. So for this input, in case if you want to do dilation, what it will do is like we kind of have a spacing between a filter here. It means let's say your filter is something like 2 3 minus 1 3. So instead of using this, it will try to keep a spacing, like it will try to enlarge your filter size like this. So by making this and then using this for convolution across your input, so by doing this way we will be able to have better like what you can say, like you can have a better reception size. Okay, so what we are doing, like this now we'll be using on top of your filter on your input, and then across like multiple windows, right? So you'll be passing this across this and then this and then this. So that way you'll be able to pass across the filter, and by doing this way you, and now the filter size is again changed, right? So previously if it is f, by doing this dilation now it becomes like f in both ways, right? It is f and f. So it will be f plus d minus 1 into f minus 1. So this is a d where d is your dilation. Okay, so if you do this way, you're now this is your feature size, and then your but your learnable parameters, like here if you see how many are the learnable parameters, f and f, right? The same way like previously if you use this filter size 20 minus 1 3, it is same number of learnable filters as this. These are like just added with zeros, maybe filled gaps with zeros. By doing this, like the number of elements in filter may have changed, filter size might have changed, but not actually the number of learnable parameters. Okay, so by doing this, what will be the new output size is, so out input minus f. Previously we used to have just this minus f, right? So but now the filter size is different. So this will be minus and plus s plus 2p divided by s. So this is what your final output will be. So by using this, you actually can get like what will be the estimate of the final output dimension. So and so this way actually you can, there is also a representation in terms of equation like receptive field. Okay, so effective reception field will be like previously if you uh, reception field effective n minus 1 plus d into n minus. So this, like with this kind of like way, like it will get increased, like your receptive field will get increased to this. So what will happen is, if you are using a 3 by 3 filter, for example, if you use a 3 by 3 filter with a dilation of 2, what will happen is this is equal to receptive field of 5 by 5, right? Because we are actually enlarging your filter by doing this. It means like if you have 3 by 3, you have something like this, right? So you have a receptive field, dilation of 2. It means it will start adding these as 0. So these are nothing but actually those are your values, and these are newly added, like because of dilation it will start adding like zeros to it, or maybe some values to it. Okay, so this way you are enlarging your receptive field from 3 by 3 to 5 by 5. So this is what happens in dilated convolution. Okay, we also call this as atrocious convolution. Able to have much deeper and deeper models with, like if you use a lower filters, like because you know the advantage of using a 3 by 3 filter to a 5 by 5 filter, right? So 5 by 5 has 25 parameters in it, 3 by 3 has 9 parameters in it. But in case if we are getting the advantage of using this filter just by using this, then what you'll have is but that is what like you'll be able to get like much deeper and deeper models just by using a smaller filters, right? And because like you'll have like less number of parameters as well, so you can go much deeper, but you can get the advantage of using a larger filters. Okay, so at a time you'll be able to see much bigger size of your image, rather than seeing only a small part of it. Okay, this way actually your reception field is much bigger by using a larger filters. So this is how you can get that advantage by using this dilated convolution.